Lesson 4 in Unit 3. Lesson 4 deals with extrema, which is something we've dealt with before, and it deals with the first derivative, something we've dealt with before, and it puts the two of them together in a beautiful way. That's what we're shooting for in these next 15 minutes or so. So what I'd like to do is I'd like to draw a function for you. This function looks like, this function looks, that's flat, that's flat, that's flat, that's flat, like so. So I pulled the y-axis out because it's irrelevant. That's A, that's C1, that's C2, that's C3, that's C4, that's C5, and that's B. Consider the following. In between A and C1, what do we know about the first derivative? First derivative of this function f of x. What do we know between A and C1? The first derivative is positive. And we know that the first derivative is positive because we could draw tangent lines anywhere along that curve and we would get positive slopes. Now, at C1, we're flat. And then what happens until we're flat again at C2? What do I know about f prime? I know that f prime is positive. And again, I can make the connection to yesterday's lesson. I know that f prime is positive because between C1 and C2, f of x is increasing. And since f of x is increasing, its derivative must be positive. Between C2 and C3, when we're flat again, what happens? Well, f prime is negative, and f prime is negative because f is decreasing. How about between C3 and C4? Well, f prime is again negative. So we've got a flat tan at C4, and between the flat tans at C3 and C4, f prime is negative. Well, then between C4 and C5, f prime is positive, and between C5 and C6, f prime is negative. Well, consider the following. Where are the maxes and the mins? So if you talk to some elementary calculus student, the elementary calculus student is going to say, the maxes and mins happen everywhere the derivative is 0. Well, that's not entirely true because here's a place where the derivative is 0, but that's not a max or a min, and here's a place where the derivative is 0, but that's not a max or a min. Here's a place where we have a max and the derivative is 0. Here's a place where we have a max and the derivative is undefined. But what happens at those red points? At those red points, the derivative changes from positive to negative. The derivative changes from positive to negative. Similarly, here's a min. Here's a place where the function is as low as it is in some open interval containing that point. What happens to the derivative at C4? C4 changes from negative, f prime changes from negative to positive. What happens at these points? What happens at that place where we've got a flat tan? Well, at the place where we've got a flat tan, but it's not a max or a min, the derivative is positive on the left side of it and also positive on the right side of it. And similarly, here at C3, f prime is negative on the left side of C3, and f prime is negative on the right side of C3. And so since these are all possible cases, they give us a firm foundation for what I'm going to call the first derivative test for local extrema. And this is something that we must know and must know well. And the test says something like, let f be a continuous function. There are 3 parts to the test. Part 1, if f prime changes sign from positive to negative at C, f has a local max at C. If f prime changes from negative to positive at x equals C, f has a local min at C. And if f prime does not change sign at C, f has no extremum at C. And this is exactly what the picture tells us. The picture tells us at the 2 maximum points, f prime changes from positive to negative. At the minimum, f prime changes from negative to positive. So I want to get us out of this mode that says the derivative is 0. We look for critical points. We look for places where the derivative is 0 or does not exist. And we do that so that we can look for the places where f prime changes sign. That's what matters when we're looking for extrema. Now, we've dealt almost exclusively with polynomials, and we've dealt almost exclusively with nice factorable polynomials in our previous year's work. And so we are very used to take a derivative, set it equals 0, and solve. But I want us to go a little bit more rigorous and say, I'm looking for places where the derivative changes sign. Here's what that's the learning. That's the big learning. I'm just going to demonstrate it a bit, and then we're all going home. I want to find all local extrema. How about f of x equals x cubed minus 9x squared plus 24x? Well, if I'm looking for local extrema, I'm probably going to end up taking a derivative of some kind. F prime of x is 3x squared minus 18x plus 24. I want that to equal 0. And you can factor that in the privacy of your own home, which, as we've always said, is your own privates. And you get 3 times x minus 4 times x minus 2. What does that mean? That means that on my number line, which as I imagine is a line with numbers on it, there are 2 places where that derivative could change sign. There are 2 critical points, 2 places where the derivative is 0 or undefined. That happens at x equals 2 and at x equals 4. Critical points, places where the derivative is 0 or undefined, 2 and 4. Then I think about what f prime is. F prime is a happy parabola. It starts high, goes low, ends high. If I don't know that, if the shape is unfamiliar to me, I can pick my favorite value that's less than 2. I can sub that into the derivative and figure out, okay, maybe at x equals 1, the derivative is 9, that's positive. And so the derivative will have to be positive everywhere less than 2. Similarly, I could sub in 3, find out the derivative is negative there, sub in 5, find out the derivative is positive there. So I can do it that way also. So now I've got to make a determination. I've got to make a determination about x equals 2 and x equals 4. And so here's my determination. F of 2, which is 20, you can do that just by subbing 2 into the f of x function. That is a local max. And it's a local max because what does f prime do at x equals 2? F prime changes from positive to negative at x equals 2. And that's exactly how you want to write it down. That's exactly how you want to show the work. It's a local max because f prime changes from positive to negative at x equals 2. Similarly, f of 4, which happens to be 16, is a local min because f prime changes from negative to positive at x equals 4. We should ask the question, are either of those absolute extrema? And so you know from your work, what have I got? I've got that f of 2 is 20, f of 4 is 16. I'm increasing, decreasing, increasing. Neither of those is an absolute extremum, not at all. If I may, find all local extrema for g of x is x squared ln x. X squared ln x. So how does that work? Let's take a derivative. The product rule is so much fun. It's 1 prime 2 plus 2 prime 1. That's x plus 2x ln x. And then we factor out an x. So I want that to equal 0. You get two possibilities. You get 0, and then you get whatever this gives me. So I come on off into scrapland here, and I think to myself, ln x is negative a half. And if ln x is negative a half, then I exponentiate each side. I get e to the minus 1/2. So there are two places on the number line where I could have a critical point, where I do have a critical point. One is at x equals 0. The other is at x equals e to the negative 1/2. The curious thing is that the domain of this function only runs from 0 to infinity. And so I've already got 0 outside the domain of my function to start with. And then I've got e to the minus 1/2 happening here. So I'm going to take a look at the sign of g prime, S-I-G-N sign of g prime, and I'm going to ask myself, how does this go? So I sub in my favorite number that's less than e to the negative 1/2. Maybe I sub in 0.1 or something like that, and I crunch that out, and I figure out negative. Negative. And then I sub in my favorite number that's greater than e to the negative 1/2, like 12, and I sub that into g prime, and I figure out that's positive. And so I want to answer the question. I know that g of e to the negative 1/2, and that happens to be negative 1 over 2e for those of you that want to take the time and sub that in to the g function, and pull that out. That is a local min because G prime changes from negative to positive at x equals e to the negative 1/2. It's a local min because G prime changes from negative to positive at e to the negative 1/2. That is a big deal. That's the way you want to say it. I have a local min because G prime changes from negative to positive. Is it an absolute min? Sure it is. It's an absolute min because the function decreases and then increases forever. There's never a decreasing that happens again. Is there an absolute max? I've no idea. We don't have enough knowledge to figure out if we have an absolute max anywhere yet. I suspect not, because x squared gets pretty big and ln x gets pretty big. But I do know I have an absolute min at that point also. So what do you have to know? You have to know how to find maxes and mins. You have to know if I'm using the first derivative, I want the derivative to change from positive to negative at a max and negative to positive at a min. And you have to be okay saying that. You have to be okay saying that in a testing context. All right? Wonderful. Glad you stuck with me.